So, now we would like to combine these two properties, the properties of linearity and time invariance. Okay, let us make sure we are comfortable with both of these. This property says if I take the transformation of A times x1 of n plus B times x2 of n, then what I will get is A times y1 of n plus B times y2 of n. That is the linearity property. The time invariance property says if I take the transformation of x1 of n minus n naught, then I will get y1 of n minus n naught. Of course, scaling can, if it is a linear system, scaling will also work. So, if I look at systems that satisfy both these properties and then write down the general form of the input, x of n is equal to summation k equal to minus infinity to infinity x of k delta of n minus k. This is my input. Okay. Now, I am interested in the output y of n, which is going to operate on this input x of n. Okay. Now, here comes a very important concept. I want you to pay very careful attention. Okay. Now, look at the input. The input consists of delta the unit impulse functions, which are shifted in time, okay, from minus infinity to infinity. These are unit impulses which are shifted in time. Shifted in time. These are nothing but scale factors. Scale factors. Now, if you are now looking at it as a sum of these shifted unit impulses, different scaling, if you invoke the property of linearity, if you multiply the input by a constant, output also will get multiplied by a constant. If you delay the input, output will also get delayed. Use both of these properties. Okay. So, the transformation on x of n can be written as a transformation on the summation k equal to minus infinity to infinity x of k times delta of n minus k. Okay. Now, by invoking the superposition property says two inputs, I can take the input of first input and sum of second input and add their outputs. So, using the property of superposition, I can then say that this output will be the same as the summation k equal to minus infinity to infinity, the transformation operating on each of the inputs separately, right. The sum of the inputs is going to produce for me the same as the sum of the outputs. So, outputs will be the transformation operating on x of k delta of n minus k. By the property of superposition, we have shown that this is equal to this. Okay, not an arrow, it is actually equal to this. This is the step that we have. And now go to the next step where we say this is nothing but a scale factor. This is nothing but a scale factor. Okay, scale factor. Scale factor also in a linear system, scale factor is also it's homogeneous. So, therefore, if you scale the input, the output will get scaled. So, this is the same as summation k equal to minus infinity to infinity x of k, the transformation of delta of n minus k. Okay, so, this is basically a scale factor multiplied by delta of n minus k. Now, here comes the very important one. So, if you tell me what is the output if I apply the input to this particular system, and this happens to be some sequence h of n, if this is known, okay, what will be the transformation of delta of n minus k. It will be the same output sequence which is shifted by n minus k. So, this will be equal to summation k equal to minus infinity to infinity x of k h of n minus k. Okay. So, what is it that we have done? We have asked what is the response of this linear and time invariant system to a unit impulse. Unit impulse. Okay. So, we call h of n as the impulse response. Impulse response. Now, notice that if you know what h of n is, then you can calculate the output for any input, right? Remember, any input x of k can be any sequence and you will be able to compute. So, what do you need to be able to compute the output of a linear and a time invariant system? This is going to be completely characterized by what we call as the impulse response. So, what you need to do to study LTI systems, these are called LTI, linear and time invariant systems, is to know what their impulse response is, because once you know what the impulse response is, then you get this expression. Okay. Now, what we can do is take a closer look at this expression. Y of n, the output of an LTI system, is given as summation k equal to minus infinity to infinity x of k, the input, times h of n minus k. Okay. Now, come back, use all of the tricks that we learnt in the operation of sequences. Notice that this has k is the index, right? So, you can think of it as minus k plus n. So, minus k plus n involves a shift and it involves time reversal, right? There is a time reversal and a shift involved in this expression. So, the computation of the output, computing the output of an LTI system involves the following. Okay, step 1, obtain the impulse response, obtain h of n. Okay. Then the second step is time reversal of h of n. Time reversal of h of n. And third one is shift the time reverse sequence, time reversed sequence, and for each shift you obtain the output point. At each shift obtain one output point. Obtain one output point. Okay. This is what we call the step 2 and step 3 combined is what we refer to as discrete time convolution. Okay. So, if you have two sequences, discrete time convolution, so what we are saying is the output y of n is the convolution of x of n convolved with h of n. So, what we can do is you time reverse h of n, then you shift and then compute the product and calculate the output. We will also show that this can also be written as h of n convolved with x of n. So, you can time reverse the input sequence and keep the impulse response without reversal and do exactly the same, and you will get exactly the same operation. Now, this is the analogy between a continuous time linear time invariant system. Continuous time linear time invariant system is fully characterized by the impulse response h of t. Impulse response h of t, it's continuous time signal, and the output y of t is given by the convolution of the input x of t and the impulse response h of t, which is computed via an integral. computed via an integral. Okay, and I'm sure you are very comfortable with this. This is minus infinity to infinity, x of tau, h of t minus tau. You can see the time reversal there happening, d tau. Okay, this is an integral. In the case of a discrete time system, what we have is a summation y of n, which is given by k equal to minus infinity to infinity. Just like there you have the integral going from minus infinity to infinity, the summation goes from minus infinity to infinity, x of k, h of n minus k. Same operation. So you can see the similarities between this is a discrete time LTI system. It is completely characterized by the discrete time impulse response h of n. Okay. So we have now come to a very good point where we know a lot about the properties of sequences. We know what operations we can do on sequences. We now also have an idea of the most powerful class of discrete time systems, which is those systems which will satisfy the properties of linearity and time invariance, which are completely characterized by means of the impulse response. So given any input, we can, and knowing the impulse response, we can now compute the output. Now, how do we apply it? What are some of the other properties that we can look at in the context of discrete time systems? How do we build on this knowledge? How do we build such systems? For example, if you want to build a filter which removes high frequency noise, how do you do that? That's a discrete time system. So we will start to now put together the building blocks that will help us build very practical systems. We will also be looking at how to study some of these things using some laboratory experiments, which we'll be doing as we go along with the theory. We will also be looking at some exercises that you will be doing on the computer. So again, we will stop at this point and pick it up from here and build on the understanding of what are discrete time sequences, operations of discrete time sequences, and then looking at discrete time systems and how do we put all of these together. Thank you.